Hi there. In this video, we're going to be talking about half-range series. So thus far in the videos, we've been talking about periodic functions which have the period of 2 pi. So we've been looking at functions between minus pi and pi, and we've been considering periodic functions of this nature. So what a half-range series is what happens now if we only have a function that is from 0 to pi. So that's where the half comes in. So let's just say that there is nothing defined from minus pi to 0. So we just have something between 0 and pi. So let's just say we have a function y is equal to 2x between 0 and pi. Okay, so we have f of x is equal to 2x, and this is between 0 and pi. Okay, all our work on the Fourier series thus far has been defined for specifically a period of 2 pi. So if we have a function now between 0 and pi, what do? We want to represent the Fourier series for this kind of function. We want to get a representation of the function between 0 and pi. So what do we do here? Well, the answer is that we make something up, right? So if we are only going to consider the function between 0 and pi, we could literally put anything between minus pi and 0, and we could write the Fourier series as we generally do from minus pi to pi, and it wouldn't make any difference. It wouldn't make any difference because we would just have a representation of some function between minus pi and 0, but that wouldn't matter because even if we were to try and determine values between 0 and pi, we would still get the representation of the function between 0 and pi. So the answer to the question is, what do we do? How do we write a Fourier series for a half-range series that's in that we are only given a function between 0 and pi? Well, what we do is that we literally make up something between minus pi and 0, and then we write the Fourier series as we normally do between minus pi and pi, and we just use that series as it is because it does give us the representation. So the question now is, what do we put between minus pi and 0? We can't put anything, but we saw in the previous video where we spoke about even and odd functions. So if we were to identify if a function is even and odd or odd, then we can literally simplify a lot of our work in determining the Fourier series. So the easiest thing to do when we have a half-range series is to either choose whether we want an even function or an odd function, and we write the Fourier series for whatever function we assume between minus pi and 0, and we just continue in that manner. So we can firstly assume, the first assumption is that we can assume an even function between x is between minus pi and 0. So if we assume an even function between minus pi and 0, then what happens is we assume that we have this kind of converse function. We remember that an even function is symmetrical about the y-axis. So if we put a mirror on the y-axis, we should see something on either side. So we also remember about an even function is that it has only cost terms because Bn is equal to 0. So then we'll have Bn equal to 0, and it will contain only cost terms. So that's the one thing that we can do. The other thing that we can do is we can assume an odd function. So if we were to assume an odd function between minus pi and 0, it would literally just be, we would be assuming that there is a symmetry about the point of origin. So if something is symmetrical about the point of origin, then what we're assuming is that we have this diagonal line and it's symmetrical kind of about that diagonal line. So now what would it look like if it was an odd function? We would assume that the function would look something like that. Okay? So we would assume that this is our function if it was an odd function. So in that instance, an would equal to 0. So we would assume an odd function between x is between minus pi and 0. That would mean that an would equal to 0, and then we would have only sign terms. So let's just do this as an example quickly. So let's just say now we choose that there is an even function. We are choosing to say that there is an even function between minus pi and 0. So that's the function that we are assuming. So in the last video, we looked at what the Fourier series equations become when we actually do this. So a naught would be the integral from 0 to pi of 2 over pi of f of x dx. So that's 2 over pi between 0 and pi of 2x dx. And we have done all these kinds of integrals in a lot of detail in the previous examples. So if we do this, we find that it becomes 2 pi. So a naught is equal to 2 pi. And then we also remember that bn is equal to 0, since it's an even function that we have chosen, and it has only cos terms, the Fourier series. So we only need to determine an. And an, if you would recall, from the last video when we looked at even and odd functions, it was 2 over pi, integral from 0 to pi of 2x cos x. And we've evaluated this integral in the previous videos. So you can go and look at the previous videos to see how we've did this entire things, but we need to use integration by parts to determine this. So I'm not going to redo this this entire example again. It's in the previous video if you'd like to go and look at it. But anyway, we see that an is equal to minus 8 pi over, minus 8 over pi n squared. And this is only for odd numbers. So for even numbers, an is equal to 0. So what does the Fourier series look like once we substitute all of these things? So f of x will equal to pi. Remember, it's a naught over 2. So the first, if you can just write the Fourier series quickly, it's a naught over 2 plus the sum of n starting from 1 to infinity of an cos nx plus bn sine nx So we said bn is equal to 0 since it's an even function, and we have only cos terms. So a naught over 2, so we have 2 pi over 2, so that just gives us pi. And then the remainder is minus, and then an was minus 8 over pi n squared, so we can take out 8 over pi as a common factor. So we have 8 over pi, and then we just write the cos terms. So we have cos x, and remember we have 1 over n squared, so it's only valid for odd numbers as well. So we have 1, then the next number is 3, next odd number. So we have plus 1 over n squared, so it's 1 over 9, cos 3x, and then the next odd number is 5, So we have 1 over 5 squared, so that's 1 over 25. And then we have cos 5x, and so on. So this is what the Fourier series looks like for this half-range series, and we have chosen it specifically to be this way. So we have just made up something. We have just chosen to say that there is a even function between minus pi and 0, and we've written the Fourier series for this entire thing between minus pi and pi. So it's fine, it's okay to do this because we still have a representation between 0 and pi, which is really what we are interested in. We could have also did the same thing, and we could have assumed an odd function instead, and we would have a Fourier series with only sine terms. We could also choose neither. In that case, we would have both cos and sine terms, and we would have to evaluate both an and bn. But it's generally easier to just assume an even or odd function, so we can simplify our work in that manner. So thank you very much for watching.